The epoch of Reionization, a fascinating chapter in cosmic history, occurred roughly between 400 million and 1 billion years after the Big Bang, marking a significant transformation in the universe. During this time, the first stars and galaxies began to form, and their intense ultraviolet light played a crucial role in ionizing the surrounding hydrogen gas, which had previously been neutral. This process effectively turned the universe from a dark, opaque state into a transparent one, allowing light to travel freely through space for the first time, which is why this epoch is so vital for understanding the evolution of the cosmos. Scientists believe that the reionization process was not uniform. Different regions of the universe underwent this transformation at varying rates, influenced by the density of matter and the presence of the earliest cosmic structures. One of the key questions researchers are exploring is how long the epoch of reionization actually lasted. Estimates suggest that it spanned a few 100 million years, but pinpointing the exact duration remains challenging due to the limitations of our observational data. Another point of interest is the role of massive stars and black holes during this period. These entities are thought to have contributed significantly to the ionizing radiation that drove reionization. The first galaxies, which emerged during this epoch, were likely quite different from the galaxies we see today, featuring irregular shapes and rapid star formation rates, raising questions about their structure and composition. Astronomers employ various techniques to study the epoch of reionization, one of which includes analyzing the spectral lines of distant quasars. When light from these quasars passes through the intergalactic medium, it interacts with hydrogen atoms, producing a specific absorption pattern that provides clues about the state of hydrogen at that time. This method allows scientists to infer the density and ionization state of hydrogen in the early universe, revealing how it evolved over time. Additionally, observations from powerful telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope are expected to provide deeper insights into the early galaxies and the processes that contributed to reionization. The concept of feedback also plays a crucial role in understanding the epoch of reionization, as the energy output from stars and supernovae can influence the surrounding gas, either accelerating or hindering the reionization process. This interplay between star formation and the intergalactic medium is complex, and researchers are working to unravel these relationships to better understand how the first structures in the universe evolve. Moreover, simulations that model the growth the epoch of reionization, often abbreviated as EOR, refers to a fascinating period in the history of our universe, occurring roughly between 400 million and 1 billion years after the Big Bang, during which the first stars and galaxies to emit light. This light, in turn, played a critical role in ionizing the hydrogen that filled the universe, turning it from a dark, neutral state into a hot, ionized state filled with free electrons and protons. These transformations in the universe's evolution, and it has profound implications for the structure and formation of galaxies as well as for the cosmic microwave background radiation that we can still observe today, which carries the imprint of this early cosmic timeline. It's during this epoch that the universe transitioned from being opaque to transparent, allowing light to travel freely, which enabled the illumination of the cosmos, leading us to see the vast expanse of the universe as we know it. The significance of the Eor extends beyond just the formation of stars and galaxies. It also highlights the role of feedback processes, such as the energy and radiation produced by the first stars, which influence the surrounding gas, affecting star formation rates and the growth of large-scale structures in the universe. Understanding this epoch helps astronomers piece together how the universe evolved into the complex structure we observe today. Additionally, it provides insights into the properties of the first luminous objects, including their masses, temperatures, and the types of elements they produced, which were essential for the development of subsequent generations of stars and galaxies, as well as for the chemical enrichment of the universe. The study of the Eor is ongoing, with current observations using advanced telescopes, such as the James Webb Space Telescope, which aims to peer back in time to capture the light from these early stars and galaxies, helping us to map out the timeline and understand the processes that fueled this remarkable period in cosmic history. Is not just a milestone in the story of the universe, but also a key to unlocking the mysteries of cosmic evolution. The epoch of Reionization, a significant period in the history of the universe, took place roughly between 400 million and 1 billion years after the Big Bang, which occurred about 13.8 billion years ago. During this time, the universe transitioned from being opaque to transparent as the first stars and galaxies formed and began to emit light, ionizing the surrounding hydrogen gas. This process marked the end of the cosmic dark ages, a time when the universe was filled with neutral hydrogen and lacked any sources of light. The Reionization period is crucial for understanding how the universe evolved, as it set the stage for the formation of larger structures, like galaxy clusters, which we observe today. Observations suggest that the epoch of Reionization likely peaked around 750 million years after the Big Bang, during which the universe became significantly brighter as more stars ignited, and the first galaxies began to emerge. The exact timeline and duration of this epoch are still subjects of research, with astronomers using advanced telescopes like the Hubble Space Telescope and, more recently, the James Webb Space Telescope to study the light from distant galaxies and gather clues about the conditions of the universe during this transformative era. This period not only provides insight into the formation of the first cosmic structures, but also raises intriguing questions about the nature of dark matter and dark energy, which play significant roles in the overall evolution of the universe. As scientists continue to investigate this epoch, they aim to understand the processes that govern star formation, galaxy evolution, and the interactions of different cosmic components during this critical phase of the universe's timeline. The epoch of Reionization is, therefore, a fascinating area of study, shedding light on how the universe became the vast and dynamic cosmos we observe today, filled with billions of galaxies, stars, and planets, all evolving under the influence of fundamental forces. Before the epoch of Reionization, or Eor, which began roughly 400 million years after the Big Bang, the universe was a vastly different place, filled with a darkness that stretched across the cosmos, as it was primarily made up of hydrogen and helium gas, along with dark matter, this time known as the Cosmic Dark Ages. Followed the formation of the first atoms, when the universe cooled enough for electrons to combine with protons to form neutral hydrogen. And it was a period marked by the absence of light, as no stars or galaxies had yet formed to illuminate the vast emptiness. During this phase, the universe was a cold, dim expanse, where radiation from the Big Bang, known as the cosmic microwave background radiation, was still detectable, providing a faint glow. But overall, the universe remained very quiet, with only small flux lead to the formation of structures. The conditions were also characterized by a smooth and homogeneous distribution of matter, with slight variations in density, which would serve as the seeds for the future formation of stars and galaxies. The gravitational forces acting upon these density fluctuations began to pull matter together, leading to the formation of the first structures. But this process was incredibly slow, as the universe was still expanding. During this time, cosmic inflation had already occurred, stretching the fabric of space-time and smoothing out irregularities, allowing for a uniform distribution of matter. But as time passed, regions of higher density began to collapse under their own gravity, paving the way for the first stars and galaxies to form. As these early stars ignited, they emitted light and heat, which was crucial in transforming the surrounding hydrogen gas. The intense radiation from these stars began to ionize the hydrogen, stripping electrons away and creating a more complex environment, which ultimately led to the end of the Dark Ages and the start of the Eor. This transition marked a critical turning point in cosmic history, as the universe transitioned from a featureless void to a dynamic, illuminated space filled with the first celestial bodies. It is during this time, prior to the Eor, that the universe was also undergoing significant cooling as it continued to expand, leading to the formation of structures that would eventually evolve into galaxies. The temperature of the universe at this stage was much lower than it had been in its early moments, but still high enough to prevent the formation of stable structures, and it wasn't until the first stars began to shine. The end of the Dark Ages, in relation to the era of Reionization, or Eor, is a fascinating topic, as it marks a significant transition in the history of the universe. Many cosmologists and astronomers agree that the Dark Ages began after the cosmic microwave background radiation was released, about 380,000 years after the Big Bang. During this time, the universe was filled with neutral hydrogen and very few sources of light, hence the term Dark Ages. This period lasted until the first stars and galaxies began to form, leading to the Eon, which is estimated to have occurred roughly between 400 million and 1 billion years. After the Big Bang, during the Eon, the first luminous objects, such as stars and galaxies, began hydrogen gas, transforming the universe from a dark, neutral state into a bright, ionized one. This ionization allowed light to travel through space more freely, ending the prolonged darkness of the universe. Astronomers define the end of the Dark Ages as the point when the universe became reionized. The process is thought to have been initiated by the formation of the first stars, which emitted intense ultraviolet radiation, leading to the reionization of hydrogen gas, significant for the history of the universe, but also for the formation of structures, as the light from these early stars and galaxies allowed for the gradual cooling and clumping of matter, paving the way for the formation of larger cosmic structures, such as galaxy clusters. By studying the light from distant quasars and galaxies, researchers can trace the timeline of reionization and better understand how quickly it occurred. It is believed that this process took place over several 100 million years, with some regions becoming ionized earlier than others, leading to a patchy reionization that varied across the universe. In addition, the end of the Dark Ages is also tied to the emergence of more complex structures, including the formation of galaxies and clusters, which eventually led to the universe we observe today. The end of the Dark Ages signifies not just a transition from darkness to light, but also a pivotal moment in the evolution of the cosmos, as these first stars and galaxies were crucial for the chemical enrichment of the universe. They produced heavier elements through nuclear fusion, which would later play a significant role in the development of planets and life as we know it. This transition is studied using advanced technology such as the Hubble Space Telescope. First stars, often referred to as population, II stars, played a crucial role in the reionization process of the universe, which occurred approximately 1 billion years after the Big Bang. These stars were the first to form from primordial gas, composed almost entirely of hydrogen and helium, and their formation marked a significant turning point in cosmic history. As they ignited, these massive stars, which were much larger and hotter than most stars we observe today, began to undergo nuclear fusion, creating heavier elements like carbon, nitrogen, and oxygen in their cores. When these stars reached the end of their lives, they exploded in supernova, releasing enormous amounts of energy and these newly formed elements into the surrounding space. This process of stellar nuclear synthesis and subsequent supernova explosions had a profound impact on the intergalactic medium. The intense ultraviolet radiation emitted by these early stars played a key role in ionizing the surrounding hydrogen gas. Before their formation, the universe was filled with neutral hydrogen, which absorbed light and prevented it from traveling freely. However, the ultraviolet photons from the first stars had enough energy to strip electrons from hydrogen atoms, thus ionizing them and transforming the neutral hydrogen into ionized hydrogen or plasma. This process is what we refer to as reionization, and it was essential for making the universe more transparent to light. As more and more of these first stars formed and exploded, the cumulative effect of their radiation and the chemical enrichment they provided led to a significant change in the composition and state of the universe. The reionization process not only altered the physical properties of the intergalactic medium, but also paved the way for the formation of galaxies, clusters, and other cosmic structures that we observe today. It is believed that this period of reionization lasted for several 100 million years, and during this time, the universe transitioned from being opaque to becoming more transparent, allowing light from distant galaxies to travel across the vast expanses of space. This transition is crucial for our understanding of the early universe and the evolution of cosmic structures, as it sets the stage for the galaxies we see today. Interestingly, the exact timing and nature of reionization are still subjects of active research. Astronomers are using advanced telescopes to gather data on the light emitted from galaxies that formed during this epoch. By examining the spectra of distant galaxies, scientists hope to determine when reionization occurred and how it unfolded. The study of the formation of the first galaxies, which began around 400 million years after the Big Bang, played a crucial role in a process known as reionization, a key event in the evolution of the universe. Initially, the universe was a hot, dense fog of hydrogen and helium, making it opaque to light. As the first stars ignited within these nascent galaxies, they began to emit intense ultraviolet radiation. This radiation was powerful enough to ionize hydrogen atoms, stripping electrons away and creating free protons. The light from these early stars, along with the energy from supernova explosions, flooded the universe, gradually heating and ionizing the surrounding hydrogen gas. As more galaxies formed, their collective brightness increased, leading to a significant rise in the density of ultraviolet light across the cosmos. This influx of energy contributed to the gradual clearing of the universe, allowing light to travel freely. The ionization bubbles created by the light from these galaxies expanded, eventually overlapping with one another, which marked the end of the cosmic dark ages. By the time the universe was about 1 billion years old, it is believed that reionization was largely complete, resulting in a universe filled with hot, ionized gas, which set the stage for the structures we see today. Research using data from the Hubble Space Telescope, as well as observations from ground-based telescopes, has revealed that the first galaxies were not only small and numerous, but they also had significant star formation rates. This intense star formation led to the production of more ultraviolet light, which further fueled the reionization process. Scientists theorize that it was the combination of many small galaxies merging to form larger structures that contributed to the rapid increase in ionizing radiation. Furthermore, simulations of the early universe suggest that the environment surrounding these galaxies played a significant role in reionization, with factors such as gas density and temperature influencing how quickly and efficiently the ionization occurred. As galaxies interacted with their surroundings, the dynamics of gas flow and gravitational effects would have accelerated the process, enhancing the overall contribution to reionization. The study of reionization helps astronomers understand the transition from a dark, neutral universe to one filled with light and structure, which is crucial for comprehending the evolution of galaxies and the formation of larger cosmic structure. Observing distant galaxies, especially those from the epoch of reionization, provides insights into the conditions and processes that shaped the early universe, and highlights the importance of the first galaxies in transforming the cosmic landscape during the epoch of reionization. 2 has the Eeyore. The first stars and galaxies began to form, and with them they emitted various types of radiation that played a crucial role in the evolution of the universe. These early celestial bodies primarily emitted ultraviolet radiation, which was significant in reionizing the surrounding hydrogen gas that had cooled and condensed after the Big Bang. This ultraviolet light, with its high energy, was able to ionize hydrogen atoms, stripping electrons away and creating free protons, effectively changing the state of the universe from one mostly filled with neutral hydrogen to one filled with ionized hydrogen. In addition to ultraviolet radiation, these early stars also emitted X-rays, which contributed to the heating of the surrounding gas, further influencing the dynamics of the intergalactic medium. The intense energy output from massive stars, particularly those that ended their life cycles in supernova explosions, added to the cosmic radiation environment, dispersing heavy elements and radiation into the surrounding space. Moreover, when we consider the types of stars that existed during this period, massive stars, often referred to as population II stars, were among the first to shine. They were much larger than the stars we see today and produced significant amounts of radiation, including gamma rays, which are among the most energetic forms of electromagnetic radiation. This gamma radiation, albeit less common, also had an impact on the surrounding environment, influencing the formation of new structures in the universe. It's crucial to note that the wavelengths of this radiation varied, with ultraviolet and X-rays playing particularly important roles, while gamma rays represented the extreme end of the spectrum. The interaction of this radiation with the surrounding matter was fundamental in shaping the early universe, as it contributed to the ionization processes and the subsequent formation of galaxies and cosmic structures that we observe today. The energy released during these processes also affected the temperature and density of the intergalactic medium, creating regions of varying ionization that would eventually lead to the large-scale structure of the universe as we know it. Understanding the types of radiation emitted by the first stars and galaxies during the ER not only provides insight into the conditions of the early universe, but also helps astronomers and physicists piece together the complex puzzle of cosmic evolution. The interplay between these different types of radiation and the matter in the universe set the stage for the rich tapestry of cosmic history that followed, influencing everything from galaxy formation to the distribution of elements throughout the cosmos. To estimate the redshift at which reionization began Astronomers rely on a combination of observational data, theoretical models, and careful analysis of the universe's evolution. Reionization refers to the period in the early universe, roughly between redshift values of 6 and 12, when the hydrogen gas that filled the universe became ionized again, following the initial recombination era when it had cooled. Enough to allow electrons to combine with protons, forming neutral hydrogen. To pinpoint when reionization began, scientists look at the cosmic microwave background radiation, or COM, which provides a snapshot of the universe when it was about 380,000 years old, and analyze the polarization patterns found in this ancient light, which are of electrons during the reionization phase. Moreover, observations from large telescopes such as the Hubble Space Telescope have been instrumental in identifying high-redshift galaxies and quasars, which emit light that can be used to trace the state of the intergalactic medium at various points in time. By studying the absorption features in the spectra of these distant objects, astronomers can determine how much hydrogen was neutral and how much was ionized, revealing clues about the ionization state of the universe at different redshifts. The Lyman Alpha forest, a series of absorption lines in the spectra of distant quasars, provides additional information about the density of neutral hydrogen in the universe, allowing researchers to create models that estimate the timing of reionization. Further, simulations of galaxy formation and evolution, along with observations of the faintest galaxies, which are believed to be among the first to form, help scientists understand the sources of ionizing radiation, such as early stars and black holes. These sources are crucial in determining when reionization would have started, as they produce the ultraviolet light necessary to ionize hydrogen. Studies of the distribution and characteristics of these early sources, combined with theoretical models of how they interact with their environment, contribute to a more accurate estimation of the redshift at which reionization began. Recent discoveries, including the identification of galaxies that existed around redshift 6, suggest that reionization was a more complex process that may have involved multiple sources and events, rather than a single moment in time. Additionally, the James Webb Space Telescope, launched in late 2021, is expected to provide unprecedented insights into the era of reionization, as its advanced instruments are designed to observe the faint light from the first studying the epoch of reionization, often referred to as a fascinating endeavor, as it marks a crucial period in the history of the universe, when the first stars and galaxies formed and began to ionize the hydrogen that filled the cosmos, making it more transparent to light. To investigate this significant epoch, astronomers utilize a variety of observational techniques, each providing unique insights into the conditions and processes that characterize this formative time. One primary method is the use of radio telescopes, which can detect the faint signals emitted by hydrogen atoms in the early universe. The 21-centimeter line, a specific wavelength of radiation emitted by neutral hydrogen, is particularly important, as it allows scientists to trace the distribution and density of hydrogen during the Eon. Projects like the Low Frequency Array, or LOFAR, and the Square Kilometre Array, or SCAR, are designed to capture these signals, offering a glimpse into the state of the universe billions of years ago. Another important observational technique involves deep field imaging, particularly in the infrared spectrum, which allows astronomers to observe distant galaxies that formed soon after the Big Bang. Space telescopes, like the Hubble Space Telescope and more recently the James Webb Space Telescope, play a vital role in this area. By focusing on very faint light from these distant galaxies, scientists can estimate their redshifts, which, in turn, provides information about their distances and ages. This helps to create a picture of how galaxies evolved during the Eon, shedding light on their star formation rates and the types of stars that were present. Spectroscopy is another crucial technique used to study the Eon, as it enables researchers to analyze the light from distant objects, breaking it down into its constituent colors. This process reveals the chemical composition, temperature, density, and motion of these early galaxies, offering insights into the types of elements that were being produced and how they contributed to the overall evolution of the universe. By examining the light from quasars, for example, scientists can study the intergalactic medium, including how it became ionized due to radiation from the first stars and galaxies. Additionally, gravitational lensing, which occurs when a massive object, like a galaxy cluster, bends the light from objects behind it, is another powerful tool. This technique allows astronomers to observe objects that would otherwise be too far. By studying how light is distorted around massive objects, researchers can infer the 21 cam hydrogen line, which is a specific wavelength of radio emission, arises from neutral hydrogen atoms, and it is an important tool for astronomers studying the early universe, particularly during a period known as the epoch of Reionization, or Eon. This era occurred roughly between 400 million and 1 billion years after the Big Bang, when the universe was transitioning from being opaque to transparent as the first stars and galaxies formed. Observations of the 21 cam line allow scientists to probe the distribution and density of hydrogen in the universe at that time, offering insights into how the first luminous objects influenced their surroundings. As these early stars and galaxies began to burn brightly, they emitted ultraviolet light, which had a profound effect on the neutral hydrogen that filled the universe. This radiation ionized the hydrogen, stripping electrons from the atoms, and resulted in a significant change in the state of the universe's matter. The 21 chemline observations help us track the hydrogen gas's response to this ionizing radiation. By measuring fluctuations in the intensity of the 21 cam signal across different regions of the sky, astronomers can infer the density of hydrogen, the temperature of the gas, and even the presence of the first galaxies, which are crucial for understanding how the universe became reionized. These observations are particularly challenging due to the low intensity of the 21 chem signal and the presence of foreground emissions from our own galaxy, which can obscure the faint signals from the distant universe. However, recent advancements in radio astronomy, including the development of sensitive radio telescopes like the low-frequency array LOFAR and the square-kilometre array SCAR, have made it possible to detect these signals more clearly. As researchers refine their techniques and improve their observational capabilities, they can gather more data to piece together the timeline of cosmic history during the Eor. Through the study of the 21 hydrogen line, we can also explore the conditions of the early universe, such as the density fluctuations that led to the formation of galaxies and clusters. These fluctuations are crucial in cosmology, as they provide a link between the tiny quantum fluctuations in the early universe and the large-scale structure we observe today. By analyzing the 21 line, scientists can gain insights into the physical processes that govern the formation of the first stars, the nature of dark matter, and the overall evolution of the cosmos. In summary, the 21 the cosmic microwave background, or COM, is an incredibly important relic of the early universe, and it holds key insights for understanding a period known as the epoch of Reionization. This epoch occurred roughly between 400 million and 1 billion years after the Big Bang, when the universe transitioned from being opaque to transparent, allowing light to travel freely through space. The COM itself is the afterglow radiation from the Big Bang, permeating the universe, and it provides a snapshot of the universe when it was just about 380,000 years old. A moment when protons and electrons combine to form neutral hydrogen, making the universe cool enough for without constant scattering. The significance of the COM in studying the Eor lies in the information it carries about the density fluctuations present in the early universe. These fluctuations eventually led to the formation of the first stars and galaxies, which played a crucial role in reionizing hydrogen, the most abundant element in the universe. By examining the COM, scientists can detect the temperature and polarization patterns which reflect the distribution of matter and energy in the early universe. These patterns help astronomers understand how the first structures formed and evolved over time, as the gravitational pull from these dense regions led to the birth of stars and galaxies. Moreover, the COM also provides a baseline against which we can measure the effects of reionization. As the first stars and galaxies formed, they emitted ultraviolet light, which ionized the surrounding hydrogen gas. This ionization would leave imprints on the COM, subtly altering its temperature and polarization characteristics. By comparing current observations of the COM with models of the universe's evolution, scientists can infer when and how the Eor occurred, as well as the properties of the first luminous sources. Additionally, upcoming observational missions, such as the James Webb Space Telescope, are designed to probe deeper into the universe, to gather more data on the Eor. By combining these observations with COMB data, researchers hope to create a more complete picture of the cosmic timeline, tracing the journey from the COMB to the formation of the first galaxies. This integrative approach will enhance our understanding of cosmic evolution, as it allows scientists to investigate how the processes that shaped the universe's structure and composition unfolded over billions of years. In summary, the significance of the cosmic microwave background in understanding the epoch of reionization cannot be overstated. It serves as a vital, the cosmic microwave background, often abbreviated as COMB, is a fascinating remnant radiation from the early universe, providing a snapshot of the cosmos just about 380,000 years after the Big Bang, when the universe cooled enough for protons, hydrogen atoms, allowing light to travel freely. This light, now stretched into microwave radiation due to the expansion of the universe, carries with it a wealth of information about the early conditions in the universe. One of the significant events that the COMB helps to illuminate is the epoch of Reionization, which occurred roughly between 400 million to 1 billion years after the Big Bang, a period when the universe transitioned from being neutral to ionized, primarily due to the formation of the first stars and galaxies. As the first stars began to shine, their intense ultraviolet light began to ionize the surrounding hydrogen gas, stripping electrons away from hydrogen gas. This process of ionization would gradually affect the visibility of the COMB. During the reionization period, the COMB photons encountered free electrons, resulting in a scattering process known as Thomson scattering. This scattering causes the COMB to become less uniform, creating fluctuations in its temperature. Scientists study these fluctuations in detail as they provide crucial evidence of the reionization process. The COMB's polarization patterns, particularly the B-mode polarization, can reveal the density and distribution of ionized regions throughout. Moreover, the amount of free electrons in the universe during reionization can be inferred from the COMB data, specifically through the measurement of the optical depth, which reflects how much light has been scattered by free electrons along the line of sight. Researchers have found that the COMB indicates a significant increase in the number of free electrons, suggesting that reionization was a common and widespread phenomenon. The timing and extent of this ionization event are also supported by data from other astronomical observations, such as the luminosity functions of distant galaxies, which suggest that many of these early galaxies contributed to the reionization process. Additionally, cosmic background. Radiation data from satellites like the Wilkinson Microwave Anisotropy Probe, or MAP, and the Planck satellite have provided precise measurements of the COMB's temperature fluctuations and polarization, helping scientists to build models of reionization. These models suggest that the reionization process was not instantaneous, but occurred over a significant period, with different regions of the universe ionizing at different rates, leading to a patch. Ionization fraction refers to the ratio of ionized atoms to the total region of space, particularly in the context of astrophysics and cosmology. During the early universe, specifically during the epoch of reionization, or Eeyore, the ionization fraction underwent significant changes. Initially, after the Big Bang, the universe was filled with a hot, dense plasma of electrons and protons, which meant that the ionization fraction was very high, close to 1 because most hydrogen atoms were ionized. As the universe expanded and cooled, the temperature dropped, and conditions became favorable for recombination, a process where free electrons combined with protons to form neutral hydrogen atoms. This phase occurred approximately 180,000 years after the Big Bang, leading to a decrease in the ionization fraction. As the universe transitioned from being opaque to transparent. However, after this period, as the first stars and galaxies began to form, they emitted high-energy radiation, which started to ionize the surrounding hydrogen gas again, increasing the ionization fraction during the Eeyore, which is estimated to have occurred between years after the Big Bang. The rise in ionization fraction during this time was a result of the intense ultraviolet radiation produced by these early stars and quasars, which ionized the neutral hydrogen in the intergalactic medium. The ionization fraction varied across different regions of the universe, influenced by factors such as the density of stars, the energy of the radiation, and the distribution of matter. The process of reionization was not uniform. It progressed in patches, leading to a complex structure in the ionization fraction across the cosmos. Observations from telescopes such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, aim to provide more insights into the state of the universe during this transformative era, helping scientists understand how the ionization and its impact on the formation of large-scale structures. By studying the cosmic microwave background radiation and the distribution of galaxies, researchers can infer the history of ionization fractions, which is crucial for piecing together the timeline of cosmic evolution, shedding light on how the universe transitioned from a dark, neutral state to a more ionized, luminous one, marking a significant milestone in the development of the cosmos. The relationship between cosmic structure formation and the era of reionization, often abbreviated as Eeyore, is a fascinating and complex topic in astrophysics, touching on how the universe evolved from a hot, dense state to the vast structured cosmos we observe. After the Big Bang, the universe was filled with a hot plasma of particles, predominantly hydrogen and helium, and as it expanded and cooled, this plasma eventually combined into neutral atoms, allowing light to travel freely for the first time. This period, known as the Cosmic Microwave Background, or CMB, marked a significant point in cosmic history. But following this, the universe entered a dark age, where stars and galaxies had yet to form, as gravity began to pull matter together, small. Fluctuations in density started to form the first structures in the universe, such as gas clouds, stars, and eventually galaxies. These early structures were crucial in the timeline of cosmic evolution, as they acted as the seeds from which larger formations would grow. The era of reionization occurred several 100 million years after the Big Bang, when the first stars and galaxies ignited, emitting light and radiation that reionized the surrounding hydrogen gas, which had previously been neutral. This process of reionization is closely linked to cosmic structure formation, because it was the light from the first stars and the intense radiation from early galaxies that heated and ionized the hydrogen gas in the universe. This led to the gradual clearing of the fog of neutral hydrogen, allowing light to travel further and shaping the large-scale structure of the universe as it is today. The radiation from these early cosmic structures played a pivotal role in determining how galaxies formed and evolved, influencing the distribution of matter and the formation of filaments and voids that we see in the cosmic web. Furthermore, the relationship is also reflected in the way cosmic structures evolved over time. As galaxies formed and merged, their collective gravitational influence contributed to the large-scale structure of the universe, while the process of reionization itself was influenced by the density and distribution of these structures. The feedback mechanisms between star formation and the surrounding intergalactic medium were essential to understanding how structures continued to evolve during the eon. Observational studies, using instruments like the Hubble Space Telescope and upcoming missions like the James Webb Space Telescope, are crucial in exploring this relationship further. They aim to uncover the properties of the first galaxies and stars, and how these influence the reionization process. Shedding light on the interplay between the presence of dark matter played a crucial role in the reionization process, which occurred in the universe approximately 1 billion years. After the Big Bang, during a period when the first stars and galaxies began to form, initially, the universe was filled with neutral hydrogen, which absorbed light from the newly formed stars, creating an opaque medium through which radiation could not easily travel. However, as stars ignited and began to emit ultraviolet light, they emitted high-energy photons that had the potential to ionize the surrounding hydrogen, transforming it from a neutral state into a plasma of free electrons and protons, which is what we refer to as reionization. Dark matter, while invisible and not directly interacting with electromagnetic forces, influenced the formation of structures in the universe, such as galaxies and galaxy clusters, by providing the necessary gravitational pull. The gravitational influence of dark matter helped to gather baryonic matter, which is the ordinary matter that makes up stars and galaxies, into denser regions. These denser regions acted as the seeds for galaxy formation, where the first stars could form, and the intense radiation from these stars would ultimately lead to the ionization of hydrogen. The presence of dark matter halos around these early galaxies created gravitational wells that allowed gas to cool and collapse more efficiently, facilitating the process that led to star formation. As these stars exploded in supernova, they contributed to the chemical enrichment of the surrounding medium and also emitted vast amounts of radiation, further driving the ionization process. As more stars formed in the gravitational fields of dark matter, they collectively produced enough ultraviolet light to gradually reionize the universe, transforming it from a neutral state to an ionized state. Moreover, simulations and models, such as those developed by researchers using the latest cosmological simulations, suggest that the structure formation driven by dark matter was essential in determining the timing and rate of reionization. The clustering of dark matter not only influenced where and when galaxies formed, but also affected the distribution of ionized regions in the universe. As dark matter structures grew over time, they facilitated the merging of galaxies, which created more massive stars and more intense radiation output, accelerating the reionization timeline. In essence, dark matter acted as the scaffolding upon which visible matter could assemble, leading to the formation of the first galaxies and stars, whose light would eventually ionize the neutral hydrogen. The interplay between dark matter and baryonic matter was critical, as without the gravitational influence of dark matter, the universe might have remained during the early universe. A significant event known as Reionization occurred, and it is believed that several types of astrophysicals played crucial roles in this process. Reionization, which took place roughly between 400 million and 1 billion years after the Big Bang, marked the transition of the universe from a mostly neutral state to one filled with ionized hydrogen, allowing light from stars and galaxies to travel freely through space. One of the primary contributors to reionization is thought to be the first generation of stars, often referred to as population III stars, which were massive, hot, and very bright. These stars emitted a tremendous amount of ultraviolet radiation, which ionized the surrounding hydrogen gas, contributing significantly to the reionization process. In addition to these early stars, early galaxies also played a vital role. As galaxies formed and evolved, they created environments filled with hot, young stars, which further produced ultraviolet light, helping to ionize the intergalactic medium. The merging of galaxies, along with their interactions, could have generated even more intense bursts of star formation, leading to heightened levels of ultraviolet radiation, and thus more efficient reionization. Another important source is thought to be active galactic nuclei, or agnes, which are powered by supermassive black holes at the centers of galaxies. These black holes can emit vast amounts of energy, including X-rays and ultraviolet light, especially when they are actively accreting matter. This energy output is believed to have contributed significantly to the ionization of hydrogen gas in the universe, providing another mechanism. Moreover, the role of cosmic reionization might have been influenced by the merging of dark matter halos, which facilitated the formation of stars and galaxies. As these structures merged and grew over time, they became sites for intense star formation, further fueling the ionization of the surrounding gas. There is also the possibility that other energetic phenomena, such as supernova explosions, could have contributed. Supernovae, which occur when massive stars exhaust their nuclear fuel and explode, release large amounts of energy and radiation, including ultraviolet light, into their surroundings. This energy can help ionize nearby hydrogen and other elements, thereby playing a role in the reionization process. While the exact contributions and the relative importance of these different sources are still areas of active research, telescopes like the James Webb Space Telescope are expected to provide more insight into the early universe, helping scientists the concept of feedback from early stars and galaxies plays a crucial role in the process of reionization, which is the period in the universe's history occurring roughly between 400 million and 1 billion years after the Big Bang, when the intergalactic medium transitioned from being mostly neutral hydrogen to hydrogen, allowing light to travel freely through space. This feedback mechanism primarily involves the energy and elements released by the first stars and galaxies, which significantly influences their surrounding environments, impacting the conditions necessary for reionization to occur. Early stars, known as population II stars, were massive, hot, and short-lived. They emitted intense ultraviolet radiation, which played a direct role in ionizing the hydrogen gas in their vicinity. As these stars exploded as supernovae, they released heavy elements and energy into space, creating shock waves that compressed nearby gas, triggering the formation of new stars and galaxies. This process, known as star formation feedback, creates a cycle where the energy from dying stars not only alters their local environments, but also contributes to the ionization of hydrogen over larger scales. Moreover, the winds from massive stars, which are streams of particles blown off their surfaces, can also disrupt the surrounding gas, preventing it from cooling and collapsing into new stars, thus affecting the rate of star formation. The collective energy output from these early stars and the subsequent supernova explosions contributed to heating the surrounding gas, pushing it away and creating bubbles of ionized gas, which grew and merged over time. This bubble merging process was essential for reionization, as it allowed regions of space to transition from neutral to ionized hydrogen, making it easier for light to escape and travel through the universe. These bubbles, filled with ionized hydrogen, eventually grew large enough to overlap, leading to a fully ionized universe. In addition to heating the intergalactic medium, the feedback from early stars also enriched the surrounding gas with heavier elements, which influenced the formation of subsequent generations of stars. This metal enrichment is crucial because it alters the cooling processes of gas, allowing for more efficient star formation in later epochs. The interplay between these processes means that the feedback from the first galaxies not only helped to ionize hydrogen, but also set the stage for the structural evolution of the universe, creating a dynamic environment where new stars could form, evolve, and contribute further to the reionization process. The study of this feedback mechanism provides valuable insights into how the universe transitioned from the Dark Ages. Supermassive black holes, those colossal entities that lurk at the centers of most galaxies, play a fascinating role in the cosmos, particularly in the context of the epoch of Reionization, often abbreviated as EAR. This pivotal period, which occurred roughly between 400 million to 1 billion years after the Big Bang, marks the time when the universe transitioned from being opaque to transparent, allowing light from stars and galaxies to travel freely across vast distances. Now, one might wonder, what exactly do supermassive black holes have to do with this transformative era? To understand this relationship, it's essential to look at how supermassive black holes influence their surroundings. During the EAR, the universe was filled with hydrogen gas, and the first stars, known as population IEI stars, began to form. These stars were massive and short-lived, and they produced intense ultraviolet light when they exploded as supernova. This ultraviolet light played a crucial role in ionizing the surrounding hydrogen gas, meaning it stripped electrons from hydrogen atoms, creating free electrons and protons, and ultimately led to the reionization of the universe. Now, supermassive black holes, which can be billions of times more massive than our Sun, were forming in the centers of galaxies during this time. As matter spirals into these black holes, it forms an accretion disk where it heats up and emits tremendous amounts of energy, particularly in the form of X-rays and ultraviolet light. This energy output can contribute significantly to the ionization of hydrogen in the surrounding intergalactic medium. In fact, some research suggests that the radiation from these black holes may have been an important factor in the reionization process, complementing the contributions from the first stars. Additionally, the growth of supermassive black holes is believed to be closely linked with the formation of galaxies. As galaxies formed and evolved, their central black holes grew, and the energy they emitted could have affected the temperature and ionization state of the surrounding gas. This interaction between black holes and their host galaxies creates a feedback loop, where the activity of the black hole can regulate star formation rates, influencing the overall evolution of the galaxy and its ability to contribute to the reionization process. Moreover, the presence of supermassive black holes in the early universe could have led to the formation of large-scale structures, such as galaxy clusters. These clusters would then contain vast amounts of gas that could be ionized by the radiation from simulations, play a crucial role in helping scientists understand the reionization process, which occurred in the early universe, roughly between 400 million and 1 billion years after the Big Bang. During this period, neutral hydrogen gas, which filled the universe after the Big Bang, was gradually ionized by the first stars and galaxies, leading to the universe becoming transparent to light. To unravel the complexities of this process, researchers use sophisticated computer simulations which recreate the conditions of the early universe, allowing them to explore how and when reionization took place. These simulations incorporate various physical processes, such as gravity, hydrodynamics, and radiation transfer, which are essential for modeling the interactions between matter and radiation during reionization. By adjusting parameters like the rate of star formation, the types of galaxies that formed, and the intensity of ultraviolet radiation emitted by these early stars, scientists can investigate different scenarios and their impact on the reionization timeline. Additionally, simulations help researchers visualize how the ionization bubbles grew and merged over time. As stars began to form, they emitted high-energy photons that ionized nearby hydrogen atoms, creating bubbles of ionization. These simulations illustrate how these bubbles expanded, eventually overlapping to create a fully ionized universe. By comparing the results of these simulations with observational data from telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, astronomers can refine their models and make more accurate predictions about the reionization epoch. Furthermore, simulations also provide insights into the role of massive stars, supernovae and black holes in the reionization process, helping to clarify how different types of feedback mechanisms affected the surrounding environment. The simulations also explore the influence of dark matter on reionization, as dark matter halos served as the gravitational wells that attracted gas and led to the formation of galaxies. Understanding how dark matter and baryonic matter interacted during this time is vital for a complete picture of reionization. Moreover, simulations can test the effects of different cosmological parameters, such as the rate of cosmic expansion and the density of matter in the universe, which may have influenced the timing and efficiency of reionization. By creating a myriad of models, scientists can identify which scenarios align best with current observations, leading to a more comprehensive understanding of cosmic history. Through these detailed simulations, researchers can also study the large-scale structure of the universe, observing how the distribution of galaxies and ionized regions shaped the cosmic web. This helps in establishing modeling the epoch of reionization, often referred to as the Eor, presents a myriad of challenges, primarily due to the complex nature of the universe during this transformative period, which occurred roughly between 400 million and 1 billion years. One of the key challenges is the limited observational data available, as the Eor corresponds to a time when the universe was still relatively small and light from early galaxies, which is crucial for understanding this era, is exceedingly faint, making it difficult for current telescopes to detect. This scarcity of direct observations means that scientists often rely on indirect measurements, simulations and theoretical models, which can introduce uncertainties and biases in the results. Another significant challenge is the difficulty in accurately modeling the ionization processes that occurred during the Eor, as it involved the interaction between the first stars and galaxies, which emitted intense ultraviolet radiation and the surrounding hydrogen gas. Understanding how these early sources of light influence the state of hydrogen in the universe requires a deep comprehension of both astrophysical processes and the physics of ionization, which can be complicated by the influence of various factors, including the distribution of matter, the clumping of gas, and the presence of dark matter. Furthermore, the cosmic microwave background radiation, which provides a snapshot of the universe at a much earlier time, also poses challenges for modeling the EOR. The EOR generates secondary anisotropies in the cosmic microwave background, and disentangling these signals from the primary fluctuations requires sophisticated statistical techniques and a strong theoretical framework. As scientists strive to improve their models, they must also confront the issue of cosmic variance, which refers to the statistical uncertainty that arises from observing only a limited portion of the universe. This makes it challenging to draw definitive conclusions about the overall state of the universe during the EOR, as different regions may exhibit different properties. Moreover, the methods employed to simulate the EOR often rely on assumptions that can significantly influence the outcomes, such as the efficiency of star formation in the early universe and the characteristics of the first galaxies. These assumptions must be carefully scrutinized and validated against observational data whenever possible. But the inherent uncertainties in the properties of those early stars and galaxies can lead to a wide range of possible scenarios. This wide range of possibilities complicates the task of reaching a consensus about the nature of the EOR and its implications for the evolution of the universe. Additionally, the presence of foreground contamination from our own galaxy. The ionization history of the universe is a fascinating subject, as it reveals how matter and radiation interacted over cosmic time, shaping the universe we observe today, and different cosmological models present various interpretations of this history. In the standard model of cosmology, known as lambda cold dark matter, or LDUM, the universe underwent several key phases of ionization, beginning with the hot, dense state shortly after the Big Bang, where photons, electrons, and protons were all entangled that filled the universe. As the universe expanded and cooled, this plasma eventually cooled enough for electrons to combine with protons, forming neutral hydrogen atoms in a phase known as recombination, which occurred roughly 380,000 years after the Big Bang. This event marked the decoupling of matter and radiation, allowing light to travel freely through space, creating the cosmic microwave background radiation we can still observe today. In alternative cosmological models, such as those that propose a varying speed of light or modifications to dark energy, the ionization history can differ significantly. For instance, some models suggest that the recombination process might have occurred earlier or later, depending on the parameters of the model, which in turn would influence the formation of the first stars and galaxies. The rate at which ionized regions of hydrogen and helium formed in the early universe could vary based on the density of matter and the dynamics of dark energy, leading to different timelines for the reionization of the universe. Reionization, which occurred about 1 billion to 1.5 billion years after the Big Bang, is the process where the universe transitioned from being mostly neutral to a state filled with ionized hydrogen, again influenced by the first light from stars and galaxies. Moreover, in models that include more complex physics, such as those incorporating the effects of primordial magnetic fields or exotic forms of dark matter, the ionization history might show deviations from the standard predictions. These changes could lead to different signatures in the cosmic microwave background, as well as in the distribution of galaxies and the large-scale structure of the universe. Some theories even suggest that the presence of massive primordial stars, known as population II stars, could have reionized the universe earlier than previously thought, causing a shift in the ionization timeline that would affect our understanding of galaxy formation and evolution. The implications of these diverse models extend into the realm of observational astronomy, as researchers utilize data from telescopes like the Hubble Space Telescope, high-redshift quasars, which are extremely bright and distant objects powered by supermassive black holes. Evidence regarding the epoch of reionization, or Eor, a period in the early universe when the first stars and galaxies formed, and the intergalactic medium transitioned from being neutral to ionized. Researchers observe these quasars, which can be seen from more than 12 billion light-years away, to gather valuable insights into the conditions of the universe during this critical phase. One of the key pieces of evidence comes from the absorption spectra of the light emitted by these quasars. As the light travels through the universe, it encounters hydrogen gas, and some of this light is absorbed at specific wavelengths, leading to what we call the Lyman Alpha forest. The presence of these absorption lines allows astronomers to measure the density of neutral hydrogen in the intergalactic medium at different redshifts, revealing how it changed over time. At higher redshifts, scientists find that the number of absorption lines increases, indicating a greater density of neutral hydrogen. This suggests that the universe was predominantly neutral before the first stars ignited and began to ionize the surrounding hydrogen, marking the end of the Eor. Additionally, high-redshift quasars have been crucial in studying the ionization state of the intergalactic medium. By analyzing the brightness and spectrum of these quasars, researchers can infer the amount of ionizing radiation that must have been produced by the first galaxies and stars to account for the level of ionization observed. Furthermore, the discovery of particularly high redshift quasars, such as those found in the Sloan Digital Sky Survey, has pushed the boundaries of our understanding, showing that these massive objects existed just a few 100 million years after the Big Bang. This rapid formation of quasars indicates that the first black holes formed and grew much earlier than previously thought, suggesting that the Eor happened sooner than expected. Observations from facilities like the Atacama Large Millimeter Submillimeter Array or ALMA, provide deeper insights into the cosmic dawn, highlighting the interplay between quasars and the surrounding environment, as they likely contributed a significant amount of ionizing radiation that helped to reionize the universe. Moreover, the study of the polarization of the cosmic microwave background radiation, combined with data from high-redshift quasars, supports models of reionization that suggest a complex interplay between star formation, quasar activity, and the reobservations of Lyman Alpha emitters, galaxies that emit light at the Lyman Alpha wavelength, are vital for understanding the epoch of reionization, often abbreviated as Eor, a period in the universe's history roughly between 400 million and 1 billion years after the Big Bang, when it transitioned from being opaque to transparent. During this time, the ultraviolet light from these early stars and galaxies ionized the hydrogen gas that filled the universe, creating the conditions we see today, where light can travel freely through space. When astronomers observe Lyman Alpha emitters, they are essentially looking at the light that has been emitted by hydrogen atoms in these early galaxies, with the Lyman Alpha line corresponding to a specific transition of an electron in hydrogen, and this emission is sensitive to the surrounding conditions, including the density and temperature of the intergalactic medium, which was primarily neutral hydrogen before reionization began. By studying the properties of these emitters, such as their brightness, how they are distributed in space, and how their light is affected by the intervening gas, scientists can infer important details about the state of the universe during the Eor. For instance, the strength of the Lyman Alpha emission can indicate how much neutral hydrogen is present, which can help researchers understand the timing and progression of reionization, as well as the influence of star formation within these galaxies on their surroundings. Moreover, the redshift of the observed Lyman Alpha light tells astronomers how far away these galaxies are, allowing them to probe deeper into the history of the universe. Additionally, the analysis of Lyman Alpha emitters can reveal information about the ionization state of the intergalactic medium, as the emission can be absorbed by neutral hydrogen, which means that the presence of significant amounts of neutral hydrogen along the line of sight can diminish them. Observed Lyman Alpha signal. A signal fact. Distribution of neutral hydrogen in the universe, offering insights into the structure of the universe at that time and the processes that led to reionization. Furthermore, the clustering of Lyman Alpha emitters can indicate the distribution of matter in the early universe, helping to trace the formation of large-scale structures, such as galaxy clusters and filaments, that formed as matter coalesced under gravity. As researchers gather more data from powerful telescopes, like the Hubble Space Telescope and the upcoming James Reionization, a significant event in the history of the universe, refers to the process that occurred roughly 1 billion years after the Big Bang, when the first stars and galaxies began to form and emit light, subsequently ionizing the surrounding hydrogen gas, which had remained neutral since the universe's infancy. This transition from a neutral state to an ionized one had profound implications for the formation of large-scale structures in the universe, influencing the distribution and evolution of galaxies, galaxy clusters, and cosmic filaments. During the era of reionization, the intense radiation from the first generations of stars and galaxies played a crucial role in shaping the cosmos. As these early celestial bodies formed, their ultraviolet light flooded the universe, heating and ionizing the surrounding hydrogen gas. This process not only created bubbles of ionized gas in an otherwise mostly neutral universe, but also affected the gravitational dynamics of the ionized regions, allowed for greater visibility and interaction among the forming structures, ultimately influencing how matter clustered together under the force of gravity. The implications of reionization extend beyond just the immediate effects on hydrogen gas. It also affected the formation of dark matter halos, which are essential for galaxy formation. Large-scale structures, including the vast cosmic web of filaments and voids, began to take shape during this time, as the gravitational pull of dark matter facilitated the gathering of regular matter into denser regions. The ionized bubbles created by the first stars and galaxies allowed for more efficient cooling of gas, which is crucial for star formation. Consequently, as these structures evolved, they became the seeds for the galaxies and galaxy clusters we observe today. Furthermore, the end of reionization marked a pivotal moment in cosmic history, as it influenced the subsequent distribution of galaxies across the universe. The regions that remained neutral were less conducive to star formation, resulting in a patchy distribution of galaxies. This unevenness is observable today, as we see some areas of the universe densely populated with galaxies, while others remain relatively empty, a phenomenon attributed to the conditions set during the reionization era. The study of reionization thus provides valuable insights into the timeline of cosmic evolution, helping astronomers understand how the universe transitioned from a dark, uniform state to the rich, structured cosmos we see now. Observations of distant galaxies through powerful telescopes allow scientists to glimpse this era, as light from those early stars travels vast distances to reach us. This light carries with it information about the conditions of reionization, a significant phase in the early universe, profoundly influences the thermal history of the intergalactic medium, or igium, which is the vast, mostly empty space between galaxies. This process, which occurred roughly between 400 million to 1 billion years after the Big Bang, marks the transition of hydrogen from a neutral state to an ionized state to an ionized state. As the first stars and galaxies formed, they emitted high-energy ultraviolet light, which ionized the surrounding hydrogen gas, creating bubbles of ionized hydrogen in the otherwise neutral igium. This transition not only changed the state of matter in the universe, but also affected its thermal properties, leading to a complex interplay of heat and cooling processes. During reionization, the energy from the ultraviolet radiation heated up the igime, raising its temperature significantly. Before reionization, the igime was relatively cool, with temperatures around 10,000 Kelvin. But as ionizing radiation flooded the universe, the temperature surged, often reaching hundreds of thousands of degrees in some regions. This heating affects the dynamics of matter and energy in the universe. As hotter gas expands, while cooler areas might collapse under their own gravity, leading to the formation of new structures like galaxies and clusters. Moreover, the ionization of hydrogen creates a change in the opacity of the EM. As the universe became ionized, the igime became more transparent to radiation, allowing light from distant galaxies to travel through it more freely. This transparency plays a crucial role in the thermal history of the igime, as it allows for the escape of high-energy photons that can further interact with the gas, influencing its thermal evolution. The resulting changes in temperature and ionization levels also affect the rate at which stars can form, as the conditions within the igime dictate the cooling processes necessary for gas to collapse into star. Additionally, the feedback mechanisms from the first stars and galaxies, including supernova explosions and stellar winds, introduced more energy into the igime, further complicating its thermal history. These events can shock, heat the gas, disrupt the cooling processes, and even cause the ejection of gas back into the igime, leading to a cyclical effect where the heating and cooling processes are continuously influenced by the evolving cosmic landscape. As reionization progressed, different regions of the universe experienced varying temperatures and ionization levels, leading to a patchy reionization process. This uneven distribution of hot and cold regions affects the large-scale structure of the universe, as reionization, a fascinating epoch in the history of the universe, refers to the process that reionized the hydrogen gas that filled the cosmos after the Big Bang, state to an ionized one, and this phenomenon occurred roughly between 1 billion and 3 billion years after the Big Bang. The phases of reionization can be broadly categorized into several stages, each characterized by distinct physical processes and conditions in the universe. Initially, after the universe cooled sufficiently, it allowed for the formation of neutral hydrogen atoms during the recombination phase, leading to the cosmic dark ages, which lasted until the first stars and galaxies began to form. The emergence of these first luminous objects, primarily massive stars and quasars, marked the beginning of the reionization process, as their intense ultraviolet radiation ionized the surrounding hydrogen gas. The first phase of reionization is considered to be the early reionization phase, where the first stars, often referred to as population II stars, began to shine, releasing copious amounts of ultraviolet light. This light had a significant impact, as it started to ionize the nearby hydrogen, leading to the formation of small ionized bubbles around these stars. As more stars formed and began emitting radiation, These bubbles expanded, eventually overlapping with each other. This expansion marked the transition to the overlap phase, which is characterized by a rapid increase in the volume of the universe that became ionized as the ionized regions grew and merged into a connected ionized medium. During this overlap phase, the density of ionized regions increased dramatically, and this is where the universe began to transition into a state where most of the hydrogen was ionized. The process accelerated as the number of stars and galaxies continued to rise, and the radiation from these sources became more prevalent. This phase is crucial because it allowed for the gradual filling of the universe with ionized hydrogen, which dramatically altered the conditions of the intergalactic medium. As the overlap phase continued, the universe entered what is known as the late Reionization phase, where ionization was nearly complete and the remaining neutral hydrogen became increasingly sparse. At this stage, the ionizing radiation from more evolved structures, such as galaxies and their active galactic nuclei, played a pivotal role in completing the reionization. This late phase is characterized by an increasingly homogeneous ionized medium, as the last pockets of neutral hydrogen were ionized, leading to a significant change the timing of reionization, which occurred roughly between 400 million and 1 billion years after the Big Bang, has a significant impact on the observable universe we see today. Reionization is the process that transformed the neutral hydrogen gas, which filled the universe after the Big Bang, into ionized hydrogen, allowing light from stars and galaxies to travel freely through space. This period, known as the Cosmic Dawn, marks the emergence of the first stars and galaxies, which played a crucial role in shaping the large-scale structure of the universe. The timing of this event influences the observable universe in several ways. First, it determines the distribution of galaxies, as the earliest galaxies formed during reionization contribute to the overall cosmic web that we observe today. The interaction between these early galaxies, their gas and dark matter, shaped the clusters and filaments of galaxies which we see in the present universe. The gravitational effects of these early structures have continued to influence galaxy formation and evolution, leading to the diverse array of galaxies we observe. Moreover, the timing of reionization affects the cosmic microwave background radiation, or COM, which is the afterglow of the Big Bang. The process of reionization introduces additional electrons into the universe, which can scatter COM photons. This scattering affects the temperature fluctuations we observe in the COM, providing clues about the density and distribution of matter in the early universe. By studying these fluctuations, astronomers can learn about the conditions during reionization and how they influence the structure of the universe. The timing also has implications for the formation of heavy elements. During reionization, the first stars, often massive and short-lived, produced heavy elements through nuclear fusion. When these stars exploded as supernova, they spread these elements throughout the universe. This process enriched the surrounding gas with elements like carbon, oxygen, and iron, which are essential for the formation of planets and life as we know it. Thus, the timing of reionization is closely linked to the chemical evolution of the universe. In addition, the timing of reionization provides insight into the nature of dark energy. Dark energy is thought to be responsible for the accelerated expansion of the universe. And understanding how reionization fits into the timeline of cosmic events helps scientists model the influence of dark energy on cosmic expansion. Observations of distant galaxies and quasars, which can be seen only due to the light that travelled through the ionized universe, allow astronomers to, during the epoch of reionization, often abbreviated as the Eor, Metallicity, which refers to the abundance of elements heavier than hydrogen, and helium in stars and galaxies, plays a significant role in the processes that shaped the early universe, specifically in how stars formed and how the first galaxies evolved. In the very early universe, right after the Big Bang, the only elements present were hydrogen and helium, along with trace amounts of lithium. As stars formed from these primordial elements, their nuclear fusion processes created heavier elements, such as carbon, oxygen, and iron, which collectively are referred to as metals in astronomical terms. The presence of these heavier elements, or metallicity, is crucial because it influences the cooling processes of gas clouds, which are the building blocks of stars. Higher metallicity means that gas clouds can cool more effectively, allowing them to collapse under their own gravity to form in regions of the universe with low metallicity. Like those seen during the Eor, the gas was less efficient at cooling. Affected star formation rates. Consequently, the first stars, often called population II stars, were likely massive and short-lived, burning hot and bright, and producing significant amounts of ultraviolet radiation, which played a key role in reionizing the surroundings. As these massive stars exploded in supernova, they enriched the surrounding interstellar medium with metals, beginning a cycle of star formation that would continue to evolve. This enrichment allowed subsequent generations of stars to form with higher metallicities, influencing their lifetimes, colors, and the types of planets that could form around them. Moreover, metallicity impacts the feedback mechanisms in galaxy formation, where the energy and materials ejected by dying stars influence the conditions for forming new stars. The complex interplay of metallicity and star formation during the Eor ultimately helped shape the structure of the universe we observe today, with varying metallicity levels leading to the diverse range of galaxies and star systems that emerged as the universe evolved. Understanding the role of metallicity during this critical period provides insights into the formation and evolution of galaxies, as well as the conditions necessary for life to develop in the universe. The study of ancient light from distant galaxies and quasars, combined with simulations and models of cosmic evolution, continues to shed light on how metallicity played a fundamental role in the transition from a dark, neutral universe to the bright, ionized state we see today, reveals an intricate web of cosmic history that connects the first galaxies, which formed shortly after the Big Bang, had properties that were quite distinct from those of later galaxies, largely due to the conditions of the early universe. In those initial moments, as gravity began to pull together clouds of gas, the earliest galaxies emerged, characterized by their smaller sizes and irregular shapes, which contrast sharply with the more structured, larger galaxies we see today. These primordial galaxies were also much more active in terms of star formation, often forming stars at a staggering rate, which is estimated to be several times greater than what we observe in modern galaxies. This intense star formation was fueled by the abundant gas available in the early universe, allowing stars to form rapidly, leading to the creation of many massive stars that had short lifespans. Additionally, these first galaxies were mainly composed of young, hot stars with a notable lack of heavy elements. Most of the chemical elements heavier than hydrogen and helium, such as carbon, oxygen, and iron, were produced in the interiors of stars and released into space, exploded as supernovae. Therefore, the first galaxies had a much lower metallicity, meaning they contained fewer of these heavier elements, which are crucial for forming rocky planets and life as we know it. As time progressed, galaxies evolved, merging and interacting with one another, leading to the formation of larger, more complex structures, which eventually resulted in the diverse range of galaxies we observe in the present day, from spirals to ellipticals. Moreover, the environment in which these first galaxies existed was also quite different. They were often surrounded by a warm, ionized gas, known as the intergalactic medium, which influenced their development and star formation processes. In contrast, later galaxies began to experience different environmental factors, such as the presence of dark matter halos, which played a significant role in their formation and evolution, providing the gravitational pull necessary to hold galaxies together and attract more gas and dust. As the universe expanded and cooled, the interactions between galaxies became more prominent, leading to the creation of structures like galaxy clusters and groups, which further influenced the properties of later galaxies. This evolution over billions of years transformed the composition, structure, and size of galaxies, resulting in the rich tapestry of galaxy types we see today, from the majestic spirals with their elegant arms to the more chaotic irregular galaxies that during the epoch occurred roughly between 400 million to 1 billion years after the Big Bang. The universe transitioned from a state of neutrality to one filled with ionized hydrogen gas. And this process was not instantaneous. Rather, it unfolded in phases. One particularly important phase is known as the overlap phase, and its significance lies in the way it marks a critical transition in the universe's evolution. Initially, the universe was filled with a dense fog of neutral hydrogen atoms, which made it difficult for light to travel freely. However, as the first stars and galaxies formed, they began emitting ultraviolet radiation, which ionized the surrounding hydrogen. The overlap phase refers to the period during which the ionizing radiation from these early cosmic sources was strong enough to create overlapping regions of ionized hydrogen, allowing light to travel more freely across the universe. This overlap was significant because it essentially transformed the cosmos from a dark, opaque environment into a much more transparent one. As these regions expanded and merged, they allowed for the first light to permeate the universe, giving rise to what we now call the cosmic dawn. This transition had profound implications for the formation of structures in the universe, as the increased visibility allowed for more complex interactions between matter and radiation, ultimately leading to the formation of the galaxies, stars, and planets that fill our universe today. Additionally, the overlap phase is crucial for understanding the ionization history of the universe, which provides insights into the properties of the first stars and galaxies, including their masses, lifetimes, and the types of stellar populations that existed during this era. Astrophysicists study the overlap phase to learn about the reionization process, which can illuminate the conditions of the early universe and help us understand how galaxies evolved over time. Observations of distant quasars and galaxies have offered clues about the timing and duration of this phase, indicating that the universe underwent significant changes as it transitioned from the Dark Ages to a more illuminated state. The overlap phase also has implications for the cosmic microwave background radiation, which is the afterglow of the Big Bang. The reionization process influenced the temperature and polarization of this radiation, offering a unique window into the conditions of the early universe, studied through advanced telescopes and instruments today. Moreover, understanding the overlap phase contributes to our knowledge of the formation of large-scale structures in the universe, as the ionization of hydrogen played a role in the gravitational models that predict the end of the epoch of reionization, often abbreviated as the EOR, rely on a combination of astrophysical simulations, observational data, and theoretical frameworks to understand how the universe transitioned from a state of neutrality, where hydrogen atoms were not ionized, to one that was ionized, allowing light to travel freely. The EOR took place roughly between 400 million and 1 billion years after the Big Bang, marking a significant phase in cosmic history. Astronomers use various computational models to simulate how the first stars and galaxies formed and how their light contributed to ionizing the surrounding hydrogen gas, which had previously been neutral. One key aspect of these models involves understanding the properties of the first stars. often referred to as population III stars, which are thought to be massive and short-lived, producing significant amounts of ultraviolet radiation, driving the reionization process. To predict the end of the Eon, these models also consider the growth of structure in the universe, which means looking at how galaxies merge and how dark matter affects the formation of these early cosmic structures. Observations from telescopes such as the Hubble Space Telescope and the recently launched James Webb Space Telescope provide critical data on the light from distant galaxies, helping to refine these models. Researchers analyze the spectra of distant quasars, for example, to detect the absorption features caused by neutral hydrogen clouds, giving an indication of how much of the universe was ionized at different epochs. Additionally, simulations must account for the influence of cosmic feedback processes, which include supernova explosions and the energy output from active galactic nuclei, all of which can either promote or suppress star formation and influence the ionization state of the intergalactic medium. These factors are complex, and researchers use advanced computational techniques to model them accurately. By combining theoretical predictions with observational evidence, scientists can adjust their models to better reflect how the reionization process unfolds. As these models evolve, they offer insights into the timing and the mechanisms that led to the end of the Eon, which is believed to have occurred around 1 billion years after the Big Bang, when the universe was filled with a hot, ionized gas, allowing light to travel freely across vast. By studying the cosmic microwave background radiation, researchers can also glean information about the conditions of the universe during the Eon, helping to provide a broader understanding of this crucial period in cosmic history. The interplay. The concept of a Patchy reionization process, which refers to the uneven and complex manner in which the universe transitioned from being opaque to transparent as the first stars and galaxies formed, is supported by various observational evidence gathered through advanced astronomical techniques. One key piece of evidence comes from observations of high-redshift galaxies, which are galaxies that existed when the universe was still young, only a few 100 million years after the Big Bang. When astronomers examine the light from these distant galaxies, they often find that it exhibits certain absorption features, particularly in the Lyman Alpha emission line, which indicate the presence of neutral hydrogen in the intergalactic medium. This suggests that there were regions where hydrogen remained neutral, while other areas were ionized, supporting the notion that reionization was not uniform across the cosmos. Additionally, studies using the Hubble Space Telescope have revealed a significant number of Lyman Alpha emitting galaxies in different patches of the sky, with some areas showing a higher density of these emissions than others. This variation in the distribution of Lyman Alpha emitters suggests that the reionization process was likely patchy, with some regions becoming ionized earlier than others, allowing light from these galaxies to escape, while other regions remained opaque. Furthermore, the cosmic microwave background, or COM, provides another layer of evidence. Measurements from missions like the Planck satellite have detected fluctuations in the calm, which can be linked to the clumping of matter and the ionization state of the universe at different epochs. These fluctuations indicate that the reionization process was likely influenced by the clustering of galaxies and their subsequent energetic output, leading to a Patchy reionization scenario. Moreover, recent studies utilizing the Atacama Large Millimeter-Submillimeter Array, or ALMA, have identified massive dusty star-forming galaxies in the early universe whose light is partially obscured by dust, yet they still contribute to the ionizing radiation. The spatial distribution of these galaxies, often found in dense clusters, reinforces the idea that some regions experienced rapid star formation and ionization, while others lagged behind. This uneven distribution of star formation is critical evidence for the patchy nature of reionization. The discovery of quasars, extremely luminous objects powered by supermassive black holes at the centers of distant galaxies, also plays understanding reionization. Observations of these quasars have shown that they emit vast amounts of ionizing radiation, which gravitational waves, which are ripples in space-time caused by the acceleration of massive objects, have opened a new window into understanding the universe and their relationship to the study. The Eor marks a crucial period in the history of the universe, occurring roughly between 400 million and 1 billion years after the Big Bang, when the first stars and galaxies began to form and emit light, ionizing the hydrogen gas that filled the state. While gravitational waves are typically associated with cataclysmic events like colliding black holes or neutron stars, their study can also provide insights into the conditions of the early universe, including the Eor. One significant way gravitational waves contribute to our understanding of the Eor is through their potential to illuminate the nature of the cosmic structures that formed during this period. The detection of gravitational waves can help scientists understand the formation and evolution of early galaxies and the first stars, providing clues about how these massive objects influenced their surroundings and contributed to the reionization process. For instance, when black holes or neutron stars merge, they emit gravitational waves that carry information about the environment in which they formed, including the density and temperature of the surrounding matter, which are key factors in understanding the conditions present during. Moreover, gravitational waves can be used to probe the cosmic microwave background, or COMB, which is the afterglow of the Big Bang and provides a snapshot of the universe when it was just 380,000 years old. By studying gravitational waves in conjunction with COMB observations, researchers can gain insights into the density fluctuations in the early universe that ultimately led to the formation of galaxies and large-scale structures. These fluctuations influenced the rate at which hydrogen was ionized, thus playing a pivotal role in the reionization process. Additionally, gravitational waves can help refine our models of the universe's expansion during the eon. The rate of expansion and the dynamics of gravitational interactions between early galaxies, stars. Cosmic structures are crucial for understanding how the universe transitioned from a mostly neutral state to one filled with ionized hydrogen by accurately measuring gravitational waves. Scientists can improve their estimates of cosmic parameters, which in turn informs their understanding of the Reionization epoch. Interestingly, the detection of primordial gravitational waves, which would have been generated during the inflationary period right Reionization, an era in the universe's history, occurred roughly between 1 billion and 3 billion and 3 billion years after the Big Bang. Implications for our search for extraterrestrial life, as it marks a period when the universe transitioned from being mostly neutral to ionized, allowing light to travel freely through space. This change was primarily driven by the formation of the first stars and galaxies, which emitted high-energy radiation, ionizing the surrounding hydrogen gas. Understanding reionization helps astronomers grasp how the universe evolved, creating environments where galaxies could form and, eventually, where life could potentially arise. The implications of reionization in the context of extraterrestrial life are multifaceted. First, the formation of the first stars and galaxies provided the necessary chemical elements and energy sources that could lead to the development of life. Before reionization, the universe was a dark, cold place filled with neutral hydrogen, making it difficult for stars to form. Once stars began to form, they produced heavier elements through nuclear fusion, such as carbon, oxygen, and nitrogen, which are essential building blocks for life as we know it. This means that the reionization era played a crucial role in enriching the universe with the elements necessary for life. Moreover, the light from these early stars allowed for the formation of complex molecules which are fundamental for the chemistry of life. The radiation emitted during reionization could have influenced the physical and chemical conditions on nearby planets, potentially leading to habitable environments. This raises intriguing questions about whether any of these early galaxies, which emerged during or shortly after reionization, might have hosted planets with conditions suitable for life. Additionally, the study of reionization can inform our understanding of how galaxies evolve over time, including their capacity to support life. The ionizing radiation from the first stars could have shaped the atmospheres of any nearby planets, affecting their temperature and chemical composition. If researchers can identify planets that formed during this era, they might uncover environments that have the potential to support life. Furthermore, the understanding of reionization can impact our search for extraterrestrial intelligence. As we look for signals from other civilizations, knowing the timeline of star formation and the impact of ionizing radiation can help us refine our search parameters, focusing on regions of the universe where conditions were most favorable for life. Lastly, Reionization also poses questions about the types of life that might exist under different cosmic conditions. If early life forms emerged during this turbulent, the epoch of reionization, often referred to as the Eor, is a crucial phase in the history of the universe, marking the period when the first stars and galaxies formed, and as a result began to ionize, had previously been in a neutral state. This process connects deeply to the concepts of cosmic inflation and the Big Bang, both of which are fundamental to our understanding of the universe's evolution. To grasp how the Eor relates to cosmic inflation, it's important to first understand what cosmic inflation is. Cosmic inflation is a theory that proposes a rapid expansion of the universe within the first moments after the Big Bang, specifically during the first tiny fraction of a second, roughly between 10:36 and 10:30 after the Big Bang. During this period, the universe expanded exponentially, smoothing out any irregularities and establishing the conditions that would lead to the large-scale structure we observe today. This rapid expansion also stretched quantum fluctuations, laying down the seeds for the density variations that would eventually lead to the formation of galaxies and clusters of galaxies. After inflation ended, the universe continued to expand, but at a slower rate, and it entered a hot, dense phase where matter and energy were densely packed. As the universe cooled, protons and neutrons formed, leading to atomic nuclei in a process known as Big Bang nucleosynthesis, resulting in the formation of hydrogen, helium, and a small amount of lithium. For about 380,000 years, the universe remained opaque, filled with hot plasma. This period is described as the recombination epoch, where electrons combined with protons to form neutral hydrogen atoms, allowing photons to travel freely, resulting in the cosmic microwave background radiation we detect today. As the universe continued to expand and cool, the first stars began to form roughly 100 million to 200 million years after the Big Bang. This era, known as the Eor, is when the first light from stars and galaxies began to reionize the surrounding hydrogen gas, transitioning it from a neutral state back to an ionized state. The light from these early stars and galaxies had enough energy to break apart the hydrogen atoms, creating free electrons once again, which is what we refer to when we speak of reionization. The connection between the Eor and cosmic inflation lies in the initial conditions set by inflation that allowed for the formation of the first structures in the universe. The density, the epoch of reionization, often abbreviated as Eor, is a fascinating period in the history of the universe, occurring roughly between 400 million and 1 billion years after the Big Bang, when the universe transitioned from being opaque to transparent. Stars and galaxies to travel through space. As we look ahead, several potential future observations could greatly enhance our understanding of this pivotal era. One promising avenue is the deployment of next-generation telescopes, such as the James Webb Space Telescope, which, with its advanced infrared capabilities, is expected to provide unprecedented views of the early universe, allowing astronomers to detect the faint and galaxies, which may lead to new insights about their formation and the energy sources that helped drive reionization. In addition, radio observatories, such as the Square Kilometre Array, are set to revolutionize our understanding of the Eeyore by allowing scientists to study the 21 centimeter hydrogen line, which is a crucial signal from neutral hydrogen in the early universe. Observations of this line could reveal the distribution of hydrogen gas, giving us vital clues about the processes that led to the formation of the first structures and the role of dark matter during reionization. Furthermore, upcoming missions like the lunar occultation of the cosmic microwave background could also provide unique perspectives, as they will allow scientists to study how light from the cosmic microwave background, which is the afterglow of the Big Bang, interacts with the early ionizing gas, potentially shedding light on the timeline and mechanisms of reionization. Another exciting potential observation comes from the analysis of gravitational waves, which may help to uncover the dynamics of massive stellar populations during the Eeyore. By identifying the sources of these gravitational waves, researchers could learn more about the types of stars that formed and their impact on the surrounding universe. Additionally, the study of high-redshift gamma-ray bursts might provide snapshots of star formation and the chemical evolution of the universe during this time, as these bursts are linked to the deaths of massive stars and can serve as beacons of activity in the early cosmos. Moreover, the development of advanced computational models and simulations will play a crucial role in interpreting observations and enhancing our understanding of the Eeyore. By combining observational data with sophisticated simulations, scientists can create a more cohesive picture of how the first galaxies formed, evolved, and contributed to reionization. These models will help to connect the dots between disparate observations, allowing researchers the study of the epoch of reionization, often abbreviated as Eeyore, plays a crucial role in enhancing our understanding of dark energy, which is one of the most mysterious components of our universe. The Eeyore occurred roughly between 400 million and 1 billion years after the Big Bang, marking the time when the first stars and galaxies formed, and their light began to ionize the hydrogen gas that filled the universe, making it transparent to radiation. By observing the Eeyore, astronomers can gather valuable data about the early universe, particularly how matter began to clump together under the influence of gravity, which is essential for understanding the large-scale structure of the cosmos. This large-scale structure, which includes galaxies and galaxy clusters, is influenced by dark energy, a force that is accelerating the expansion of the universe. The distribution of galaxies formed during the Eeyore can provide insights into how gravity, for instance, the way galaxies are clustered together, or the voids that exist between them, can reveal patterns that help scientists understand the balance between the attractive force of gravity and the repulsive effect of dark energy. By studying the EOR, researchers can create detailed simulations and models, helping to elucidate how dark energy behaves and evolves, affecting the universe's expansion. Moreover, the cosmic microwave background radiation, which serves as a remnant from the early universe, provides a snapshot of conditions just after the Big Bang. The EOR's influence on the cosmic microwave background can lead to detectable signals that astronomers are able to study. These signals can shed light on the nature of dark energy, especially when combined with observations of galaxy formation and distribution during and after. The fluctuations in temperature and density observed in the cosmic microwave background can be linked to the physical processes that occurred during the EOR, thereby offering indirect evidence of how dark energy has played a role in the universe's expansion history. Additionally, the ongoing research in the field of astrophysics, particularly through instruments designed to detect 21-centimeter hydrogen emissions from the EOR, can provide a wealth of information. These observations can help researchers trace the ionization history of hydrogen in the universe, which is crucial for understanding the dynamics of dark energy. By analyzing the data collected from these emissions, scientists can refine their models of cosmic expansion and better understand how dark energy has influenced the rate of that expansion since the EOR. In summary, the study of the limitations of current telescopes in observing the epoch of Reionization, or EOR, are significant, and they stem from a variety of technical and physical challenges. First, it's essential to understand that the EOR occurred roughly between 400 million to 1 billion years after the Big Bang, during a time when the universe was transitioning from being opaque to transparent as the first stars and galaxies formed and began to emit light. One of the primary limitations is sensitivity, as the signals from the EOR are incredibly faint, and current telescopes struggle to detect them amidst the overwhelming brightness of other cosmic sources, such as nearby galaxies and foreground emissions. The challenge of distinguishing these faint signals from the noise is compounded by the fact that the wavelengths of light we are trying to observe, particularly in the radio spectrum, are heavily affected by the interstellar medium and the Earth's atmosphere, which can obscure or distort signals we seek to capture. Moreover, the resolution of current telescopes poses another barrier, as the structures we are trying to observe from that era are very small and spread out across vast distances. Many existing telescopes do not have the necessary angular resolution to discern these early cosmic structures, which limits our ability to gather detailed information about them. For instance, the current generation of radio telescopes, including the Very Large Array and the LOFAR, are designed to observe larger and brighter cosmological phenomena. And while they can gather some data related to the EOR, they do not have the resolution or sensitivity required to resolve the early ionized regions effectively. Another important aspect is the frequency range. The Eeyore signals are primarily located in the low-frequency radio regime, specifically between 50 and 200 megahertz. However, many existing radio telescopes have limited capabilities in this frequency range, either due to technological constraints or because they are optimized for other wavelengths. This means that they cannot fully capitalize on the faint signals that are indicative of the Eeyore, thus leaving a gap in our observational capabilities. Additionally, terrestrial interference from sources such as radio broadcasts and other human-made signals further complicates the detection of these faint cosmic signals. The Eeyore signals are easily drowned out by these stronger local signals, making it difficult for astronomers to isolate and study the ancient light from that era. Furthermore, the data processing required to analyze these signals is immense, as the amount of data generated by modern telescopes is staggering. The complexity of the epoch of Reionization, often abbreviated as Eeyore, is a significant period in the history of the universe, occurring roughly between 13.8 billion and 13 billion years ago, marking the time when the first stars and galaxies formed to transparent due to the ionization of hydrogen gas. This process had profound effects on the cosmic web structure, which is the large-scale arrangement of matter in the universe, consisting of filaments of galaxies and dark matter, along with vast voids in between. As the first stars ignited, they emitted intense radiation, which played a crucial role in ionizing the hydrogen gas that filled the universe. This ionization not only allowed light to travel freely, making the universe more transparent, but it also influenced the distribution and behavior of matter on cosmic scales. During the Eeyore, the energy from these early stars and galaxies contributed to the formation of ionized bubbles within the surrounding neutral hydrogen. These bubbles expanded and overlapped as more stars formed, creating a web-like structure. The dynamics of these ionized regions altered the gravitational attraction of matter, leading to the formation of denser regions where galaxies and clusters would eventually emerge. This process shaped the filamentary structure of the cosmic web, ensuring that areas of higher density, where galaxies are more concentrated, developed along these filaments, while the vast voids remained largely empty. Furthermore, the reionization process affected the temperature and density of the gas in the universe. As the universe became ionized, the temperature of the intergalactic medium increased, which influenced the cooling rates of gas in various regions. This cooling is critical for the formation of new stars, as it allows gas to collapse under gravity, leading to star formation. The interplay between the heating from the first stars and the cooling of gas in the cosmic web initiated a cycle that would eventually lead to the clustering of galaxies along these filaments, further enhancing the structure of the universe. The Eeyore also had implications for the types of galaxies that formed. The intense radiation from the first stars could have driven outflows of gas from their host galaxies, affecting their mass and star formation rates. This means that galaxies formed during and shortly after the Eeyore may have different characteristics compared to those that formed later. These differences contribute to the diversity of galaxy types observed today, from small dwarf galaxies to large spiral and elliptic. As researchers study the remnants of the Eeyore through the intergalactic medium, often referred to as the IGMA, is a vast, mostly empty expanse that exists between galaxies, and it plays a crucial role in our understanding of the early universe, particularly Reionization or Eeyore. This epoch occurred roughly between 400 million and 1 billion years after the Big Bang, a time when the universe transitioned from being opaque to transparent, primarily due to the formation of the first stars and galaxies. The significance of the IGM during this transformative period cannot be overstated, as it served as the environment through which the first light from newly formed stars and galaxies traveled, impacting the state of matter in the universe. As these early stars began to shine, they emitted high-energy ultraviolet radiation that interacted with the hydrogen gas in the IGM. The process of reionization refers to the ionization of hydrogen atoms, which means that the electrons that were bound to the protons in hydrogen were freed, creating a plasma state. This transition was essential, as it allowed light to propagate through the universe without being scattered, enabling the cosmos to become more transparent. The IGM acted as a canvas upon which the light from these first luminous objects painted the early universe, helping to shape its structure and evolution. Moreover, the IGM is not just a passive medium. It is filled with gravitational wells created by dark matter, which help to pull in gas and facilitate the formation of galaxies. This inflow of material into galaxies is significant because it provides the necessary resources for star formation, contributing to the richness of the cosmic web. The interplay between the IGM and these early structures also set the stage for the large-scale structure we observe in the universe today, influencing the distribution of galaxies and clusters. The density and temperature of the IGM provide important clues about the conditions during the epoch of reionization. Studies of the IGM using observations from telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope help astronomers gather data about the ionization state of hydrogen in this medium, shedding light on when and how reionization occurred. The IGM also contains traces of heavy elements which were produced in the interiors of stars and expelled into the surroundings through supernova explosions, offering insights into the life cycle of stars and the chemical evolution of the universe. Furthermore, understanding the properties of the IGM is essential for cosmologists, as it serves as a cosmic web that connects galaxies. The reionization timeline, a crucial aspect of our understanding of the early universe, is influenced by various cosmological parameters. Matter, the rate of star formation, and the properties of dark energy. These parameters, which are derived from observations of the cosmic microwave background radiation, galaxy distributions, and the large-scale structure of the universe, play a significant role in determining when and how the first stars and galaxies formed, and how their light interacted with the surrounding hydrogen gas. One of the key factors affecting reionization is the density of matter in the universe, which influences the rate at which structures form. A higher matter density leads to quicker gravitational collapse of gas clouds, resulting in an earlier formation of stars and galaxies. When these first luminous objects began to shine, their ultraviolet light ionized the surrounding hydrogen gas, marking the Observations suggest that reionization occurred between about 400 million and 1 billion years after the Big Bang, but the exact timing can shift based on the density parameter, as a denser universe could result in an earlier completion of reionization. Additionally, the star formation rate is crucial, as it determines how many ionizing photons are produced. If the star formation rate is high, more stars will emit ultraviolet light, leading to more rapid ionization of hydrogen. Conversely, if star formation is suppressed, the reionization process will be slower. This rate is influenced by various factors, including the available gas in the universe, the cooling processes that allow gas to condense and form stars, and feedback mechanisms from supernova that can either promote or inhibit star formation. The properties of dark energy. If dark energy were to be weaker, structures would form more quickly, potentially leading to an earlier onset of reionization. However, the precise effects of dark energy on reionization are still an area of active research. Moreover, cosmological simulations, which model the universe's evolution, help us understand how these parameters interact. By varying the density of matter, star formation efficiencies, and the influence of dark energy, researchers can create different scenarios for reionization. These simulations are compared to observations from telescopes, such as the Hubble Space Telescope, and more recently, the James Webb over the past 2 decades. Our understanding of the epoch of reionization, often referred to as the EOR, has undergone significant transformations. Advancements in technology, observational techniques, and theoretical models. Initially, the EOR was a somewhat mysterious phase in the early universe, believed to have occurred roughly between 400 million to 1 billion years after the Big Bang. During this time, the universe transitioned from being opaque to transparent, as the first stars and galaxies formed, emitting light that reionized hydrogen gas, which had previously been neutral. Early models suggested that this process was relatively quick, taking only a few 100 million years. But as we have gathered more data, a more nuanced picture has emerged, indicating that the reionization process likely spanned a longer period and involved more complex interactions. One of the key breakthroughs in our understanding of the EOR has come from deep field observations with powerful telescopes like the Hubble Space Telescope, which revealed an abundance of high-redshift galaxies and provided clues about their contributions to reionization. These observations showed that, contrary to earlier beliefs, a variety of sources, including massive stars in early galaxies and possibly even quasars, played a role in ionizing hydrogen. The advent of radio astronomy, particularly with facilities like the Low-Frequency Array or LOFAR and the Murchison Wide Field Array, has allowed scientists to probe the Eeyore directly through the detection of the 21-centimeter hydrogen line, offering a unique window into this epoch. Moreover, simulations have become an invaluable tool in refining our understanding of the Eeyore, as they help researchers visualize how the first stars and galaxies interacted with their surrounding gas. These simulations suggest that the Eeyore was not uniform. Instead, it likely involved spatially varying regions of ionization where dense clumps of matter formed pockets of ionized hydrogen, creating a patchy reionization process. This realization has led to a re-evaluation of the timeline and mechanisms involved, suggesting that a mix of astrophysical processes, including the effects of stellar winds and supernova explosions, contributed to the gradual heating and ionization of the intergalactic medium. Furthermore, recent findings suggest that the Eeyore might have ended later than previously thought, perhaps continuing until around 1 billion years after the Big Bang, extending the timeline and pushing the boundaries of our understanding. The role of feedback processes from early galaxy formation, such as how stellar reionization, which occurred roughly between 400 million and 1 billion years after the Big Bang, was a critical phase in the history of the universe, marking the transition from a neutral to an ionized state of hydrogen gas. This process had profound implications for the evolution of galaxies, as it shaped the very conditions under which galaxies formed and evolved. During the era before reionization, the universe was filled with neutral hydrogen, which absorbed a significant amount of ultraviolet light, making it difficult for light from young stars to travel freely. Once reionization began, high-energy radiation from the first stars and galaxies ionized the surrounding hydrogen, creating bubbles of ionized gas that expanded and eventually overlapped, leading to a fully ionized universe. This transition allowed light to travel more freely, enabling us to observe distant galaxies that formed during this time. The implications of reionization for galaxy evolution are immense. First, it likely influenced the distribution and density of gas in the universe, affecting where galaxies could form. As the neutral hydrogen gas was ionized, it became less dense, altering the gravitational pull and the conditions necessary for star formation. This means that galaxies that formed during and after the reionization epoch would have been influenced by the changing gas conditions, potentially leading to differences in their structures and the types of stars they formed. Furthermore, the energy released from the first stars, known as population II stars, contributed to the heating of the intergalactic medium and could have triggered further star formation in nearby regions, creating a feedback loop that influenced the growth of galaxies. Additionally, reionization may have played a role in the size and mass of galaxies. The increased ionization levels allowed for more efficient cooling of gas, which is essential for star formation. As galaxies formed in this newly ionized environment, they could accumulate more gas and dust, leading to larger and more massive galaxies than might have formed in a neutral universe. This process also affected the types of stars that were formed, as the higher temperatures and pressures in the ionized regions could lead to the formation of more massive stars that have shorter lifespans and enrich the surrounding medium with heavier elements when they explode a supernova. Moreover, the timing of reionization is crucial for understanding the evolution of galaxies. If reionization occurred later, it would mean that the first galaxies had more time to form and evolve before the universe became ionized. While an earlier reionization would suggest that galaxies were forming rapidly,